In this tutorial, you will design and build this USB-C power supply board. Even if you have never designed any board before, you can do it. When you get your board, it is very easy to use. Based on this table, you set these switches to select your output voltage. Here is the input and this is the output. Connect USB-C power adapter. Check if the LED for your selected voltage is on. And when we measure the output, it is 12 volts. I really hope you will find this tutorial useful and you will enjoy designing this board. Let's start. To design this board, no software installation is required. You will do everything in your internet browser. Go to EasyEDA.com. Be sure you register and log in, and we are going to use this Pro edition. Now, File, New Project. I'm going to name the project as USB-C Advanced Power Supply. Save. We can close this. And I'm going to rename our project. Okay, I'm going to copy this. And I'm going to use the same name here. And this one I'm just going to call schematic. And this one I'm going to call PCB. Okay, open this. Now I'm going to put here my company name, Federal. See, it updated. Version 1, issue 0. I'm going to put here my name, Robert Veranek. Close this. And save. Now I'm going to make it a little bit bigger because it was very small schematic page. And I will update it also down here. See, it's A3. And I'm going to name, or I'm going to put the name of the schematic directly on the schematic page. Like this. So, for example, if you print this schematic or if you make PDF of this schematic, everyone will know what is this schematic about. I will make it a little bit bigger, bold, place, and I will put it on the top of the schematic page, like this. Okay. Save. Now go to LCSC website. This is the website where we are going to find all our components. And the first one what we need is this integrated circuit for the USB power delivery. So I'm going to find it. I know this company is making very good chips. Let's have a look what they have. And I would like to use the one which supports up to 28 volts. So not this one, but this one. So this is in a very easy footprint to solder down by hand, and it is up to 28 volts. They don't have it in stock, but it's okay, we don't have to worry. So I'm going to copy this LCSC part number, and in our schematic, place, device, paste, and search. Okay, they don't have it in stock, but still we can try to use it. So place this chip into our schematic and save. I really don't like this how the chip schematic symbol looks. So I'm going to save it into my personal library. Also create new footprint. And then in my personal library, I'm going to find it. Here it is. And we are going to edit the schematic symbol. So I would like to reorder the pins to make it a little bit easier to read the schematic. So the ground is usually on the bottom, power is usually on the top. These are some pins which we will use a little bit later. I'm going to delete this. Be very careful, be sure you are using 0.1 size grid. It's very, very important. I will adjust the size of the symbol, and here I will place the V-bus pin. I will place these USB signals on the left side and these configuration pins on the right side of my symbol. I do it this way because that's how the signals usually flows in your schematic, in your circuit, and it will make your schematic easier to read. So that's why I'm changing position of these pins. Okay, I will move this a little bit down and like this. Looks good. Okay, we can save this. I can close this. Now I'm going to delete this one, and I'm going to use the one which we just created, and this looks much better. Save. I keep saving because, you know, I learned the hard way. Always when you do something new, save so you don't lose your work. I will make this nicer, and you can watch where I place the symbol. You can do it same way. We are going to open datasheet, and we are going to find reference schematic. Okay, this is going to tell us how to connect our chip. This is what we need. So I'm going to zoom in, and the first component what we need is this 1 microfarad capacitor. So save. Now go to LCSC. I'm going to find passives, capacitors, ceramic capacitors, and we are going to use capacitors from Samsung. This one. And what do we need? Do you remember? 1 microfarad. Okay, so we need 1 microfarad. Now it's very important this voltage rating. We could go up to 35, but we can use this one, 50 volts. Let's have a look what they have. And this one looks okay. Don't forget, we are designing a board which goes up to 28 volts. I'm going to copy this, and I'm going to place the capacitor into our schematic. So because the input voltage can be up to 28 volts, it is important to be very careful with all the components what we will be using in our schematic. We have to connect this capacitor between VHV and ground. So I'm going to draw this connection. and I'm going to place this power symbol. I'm going to rename it. It's going to be plus. Plus, it means it's power, plus V underscore USB. Okay, and connect the second pin of the capacitor to ground. So I'm going to use ground symbol. I'm going to connect it, and I'm going to hide this name because all the grounds are going to be exactly the same. We don't need to show the name. VBus is also connected to VHV, so I'm going to copy this, and we will connect VBus to this power net. Always when I create power net or when I create a net, I always copy and paste them. I don't manually write the names if they already exist in my schematic, so because I don't want to make mistakes. Okay, ground is connected to ground, so this is simple. It is here. Again, I'm going to just copy and paste it because it already exists in my schematic. Okay. Now we need this USB-C connector. So connectors, USB, this one is in stock. Looks good, so I'm going to copy this one, and we are going to place it into our schematic. Okay, so this is the USB-C connector. I flip it to make it look nicer and also to, face the connector the way so it's easier to read the schematic. We can connect the ground pins. This is very simple connection, and this is the shield. So the shield is also connected to ground. Okay, I'm going to copy the ground symbol and paste it here. Perfect. I will just make it a little bit nicer. I moved this at the beginning, so I can easily find the datasheet. And now we are going to connect these plus and minus, or positive and negative pins of the USB interface. Okay, this is the positive, this is the negative signal of the USB differential pair. I'm going to name these nets. We would like to name it because then when we'll be doing PCB layout, you can very nicely see what kind of signals you are routing. Okay, P, 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 M, N, N. Okay, perfect. Be sure to double check. And we need to connect these two together and these two together. Okay, now these CC pins, just connect them. This is the CC1 and CC2. Now I'm not going to draw the connection pin to pin. I'm going to just name this net, and then when we will use the same net name, also when we will draw these NATs on the chip, then these NATs will be automatically connected because they have exactly same name. So if I would like to connect these, I need to use the same names. So I'm going to copy and paste it here. And I'm going to copy this one and paste it here. Okay, CC1, 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 2, 2, 2, 2. Double check, be sure everything is correctly connected. For the USB interface, we also need protection. So circuit protection and TVS diodes. I'm going to use this one in stock, and let's check this one. I'm going to find datasheet just to see if this is a good one for USB protection. Okay, it says USB, so we can use it. Let's copy the number and place it into our schematic. They have it in stock, so that's good. And I will place them like here. Maybe move it a little bit. And press spacebar, you can rotate. Spacebar to rotate. We move it a little bit and we can connect it. Second pin goes to ground on this one and also on this one. Okay. Now V-bus. So this is the power, USB power. I'm going to copy and paste the power symbol here. And usually you would like to place some capacitors here. So I'm going to find again passives, capacitors, ceramic capacitors. Do you remember what manufacturer we use? Samsung. And we need like 100 nanofarads. 0402, 50 volts in stock. This one looks okay. So we can copy it and place it into our schematic. These capacitors are used mostly for filtering, okay? And I use two because there are two V-bus pins on the connector, so we will place one 100 nanofarad close to one pin and the other one close to the other pin. Okay. Now I've seen a note about this CC2 pin here in datasheet. Simulation E marker function. Connect 1K resistor from the CC2 pin to ground. Here. So first let's find this resistor. So passives, resistors, chip resistor. For resistors we are going to use this Uni Royale 0402. Do you remember which one? 1K. So search for 1 Okay, select it. Plus minus 1%. We would like to only see the ones they have in stock, and we can use this one. So I'm going to place it into our schematic and connect between the CC2 pin and ground. Okay. By default, maybe we don't want to have this resistor fitted. So what I'm going to do, I'm going to select it, and here I will mark no. And maybe what we can do, we can also add a note. So, to remind ourselves that if we need, we can just fit this resistor for testing. But normally we don't need this resistor. So CC2 pull down resistor should not be needed if the right cable is used. Okay, before fitting this resistor, be sure you know what you are doing. We can use black color, maybe Arial smaller, 0.1, and place. Okay. I'm going to make this NF text, and we will place it over the resistor. So this is also a note telling us do not fit this resistor. Now let's connect these configuration pins. So in datasheet, we are going to use this level configuration feature. And in datasheet, we can see for different configuration pins, we can have different output voltages. And here are some nodes. So pin 1, maybe it will need pull-up resistor. Okay, we will place pull-up resistors to 3.3 volts on all of the pins. That is safe option. So I'm going to find 10K resistor. I'm just checking these prices. Some of them are for 100 components, some of them are for one piece. I'm going to use maybe this one. Again, they don't have it in stock, but this keeps changing all the time. Or maybe JLC PCB will have them in stock. LCSC maybe. Oh, see, LCSC doesn't have them, but JLC they have them in stock. I'm going to place 3 resistors. We will connect all the 3 configuration pins to these pull-ups. It's not necessary because datasheet says configuration pin 2 and 3 they have internal pull-ups, but just in case it's always useful to have the possibility to connect also these external pull-ups if needed. And the second pin of the pull-up we need to connect to 3.3 volts. That's the voltage of the internal regulator for the chip. I actually contacted the chip manufacturer and they told me there is internal regulator, 3.3 regulator. I'm going to name these 3 nets. So this one is CFG1, CFG2, and it is also I2C clock, and this one is 3, and I2C data. Double check if they are connected correctly, and don't forget to save your schematic so you don't lose your work. Now, if you would like to support also this single resistor configuration, then we would like to provide this option configuration pin 1 to connect to ground. Somewhere here I'm going to, for example, find this 6.8 kilo ohm resistor, and we can just place it into schematic. Again, we are not going to fit it by default, but maybe later we would like to do some testing, so we would like to support it. We can use maybe this one. No, this one doesn't have the symbol and footprint. So I don't know, this one maybe. It's not really important because, you know, we are not going to fit it by default, but we can use this one. So place it. Even if we are not going to fit it by default, I still would like to use some kind of correct resistor in case we would like to fit it. So I'm going to connect it. One pin goes to CFG1. I don't like this. I will move it a little bit away because I don't like the cross connection. And the second pin is connected to ground. Okay, this moved a little bit. So make it nicer. And unfit this. Copy, paste. Okay. Let's go back to datasheet and let's have a look again at the reference schematic. So this one is for the single resistor, and this is how it looks. So connected to ground, and in this configuration we may want to support also this one, so 100 kilo ohm on VHV, not 3.3 volts. Okay, see, so let's find 100 kilo ohm resistor. Okay, and again, this is just in case. It doesn't mean we have to use this connection. We can use this one, but we would like to support it. In case we need this resistor, we can then easily fit it. So I'm going to place it. This is actually the way how you create complicated schematics. If you are not sure about some connections, you can always place there the components, just do not fit them by default, and later, okay, VHV, it is this one. Later you can then experiment. That's why we would like to unfit this one, but we would like to still have it there. Okay, if needed, we can always fit it because it is in reference schematic. Maybe we will need it. I'm going to add a note so we don't forget why we place these resistors, and everyone else who is reading your schematic then also will know why we place these resistors here. So the unfitted resistors are just for experimenting. Next, these switches. So in LCSC search for switches, deep switches. Now number of positions 3, SMD in stock, and this one looks good. Okay, this is exactly what we can use. They have symbol and footprint, so copy the part number and we can place it into our schematic. We are going to connect these config pins. So I'm going to draw these connections, and then I will show you a small trick when you do copy in the schematic. Notice there is difference if you draw this rectangle from bottom right and top left corner. So top left corner, only select the items which are inside of the square. Bottom right corner, select everything crossing. So now the ground on the other side, and the switches are connected. The trick with the selection is very useful, remember it, okay? It also works when we will be doing PCB layout. Now I'm going to name this, so again everyone who is reading your schematic or who is reading our schematic will know what is this block of schematic actually doing. So these are output voltage selection switches. I'm going to make it a little bit smaller. Okay. And I'm going to name also these two other blocks. So this one is the USB-C connector. This is what will make your schematic more professional. Add these notes, add these names, because then it's very easy to use this schematic, very easy to read this schematic and understand what is inside of this schematic. Okay. And I'm going to draw a very simple table which will explain actually how these switches work and how these switches will set the output voltage. So draw it like this, very simple table. We would like to list the config pins and then the output voltage in this table. Go to datasheet and find this table. So on the top of the table we will place names of the pins, CFG1, we can just copy it. So this one is going to be 2, this one is 3, and this is the output voltage. Okay. 9, 12, 20, 28, 5. So I will start with 5, so it's in a logical order from the smallest one or lowest one to the highest one. do you remember all the voltages? 5, 9, 12. Next one is 20 and 28. Okay. And now this. One. Copy, paste, paste. This is X and X. X, it means it can be 0, it can be 1, is okay. So 9 volts is 0, 0, 0. Again, just copy and paste. And of course, you can use Ctrl+C, Ctrl+V on your keyboard. I just use the right click so everyone can see what I'm doing. I don't want to use shortcuts, keyboard shortcuts, because then some people may not know what keys I pressed. So it's more clear if I use the right click menu. And the last row is like this. Okay. Now we still don't have this 3.3 volts. So what we need is regulator. So I'm going to find this voltage regulator. We are going to use Texas Instrument. We need 3.3 volts. Small one. For example, this one. In stock, apply. And this one looks good. So let's have a look. They have symbol, they have footprint. Let's open datasheet. It is up to 30 volts, that's good. Up to 150 milliamps. We only have like 3 10K resistors there, so 3.3 divided by 10K multiplied by 3. Okay, we only need very small current. So this is perfectly fine. So I'm going to copy this and place it into our schematic. Of course, maybe our real current in the board is going to be a little bit higher than just 10K resistors, but it's still going to be very small current what we need from the regulator, so we can use this one. We are going to connect it, so we need to again double check the data sheet. What is the recommended connection? What is datasheet saying? So 1 microfarad on the input and 2.2 microfarad on the output. We already have 1 microfarad capacitor. I'm going to double check the voltage. 50 volts, so it's correct. So we can copy this one and place it on the input side of our regulator. And on the output, we are not going to create 2.2 microfarad capacitor. We are simply going to just place 3 1 microfarad capacitors here. I don't want to add extra component into our schematic. 2.2, we will have 3 microfarad, it is okay. So I'm going to connect this. Because when you are drawing your schematic, every type of the component can make your board a little bit more expensive. So if you can use same component, then you can buy them in higher quantities. Usually it means you can get them cheaper. Okay, so the input is connected to the USB voltage, and the output will create 3.3 volts. So we just need to connect these second pins of the capacitors to ground, and we need to also connect the rest of the pins. So ground, this one is easy. And this enable pin, drive this pin low to put device into low current. It can be left floating. Okay, so theoretically we can just leave it floating, but from my experience it is always good to have option to put there a footprint in case we need to debug something or test something. So same as before, I'm going to place here this resistor, but we are not going to fit it. Always when you are designing regulators, then and if they have these enable pins, you would like to always connect these pins to a resistor so you can use it later for debugging and testing if you need. Trust me, it's very useful. Okay, so this is the 3.3 volt power block. It is finished. Looks nice. And we can save our schematic. Now this pin is not connected, so we are going to mark it as not connected. And also these pins, it means when we will be running a schematic rule check, then these pins will not be checked. We are going to connect this power good pin. So let's have a look how we need to connect it. For this A variant, active low, and it's open drain. So we need again pull up resistor. I'm going to copy this one and paste it here because it is open drain. Okay, it only can do the low level. We need the pull up to do the high level. I'm going to name this power good, and we will use it to tell the person who is using the board to tell if the output voltage is correct. So we are going to create another block which is going to be called error LED. We will use 3.3 volts for our LED. Then we need 1K resistor. Always when you are connecting LED, you need to put there series resistor. And of course we need the LED. For error we would like to use maybe red one, so I'm going to find small LED, red one, maybe from this manufacturer. Okay, actually you can use any LED. I just use this one because I used it before together with this 1K resistor, so I know the brightness is going to be correct. Because very often this series resistor, you may want to change the value based on the brightness of the LED. Be sure it is correctly connected. And I'm not going to drive it directly with this power good pin. We need to invert this. So we are going to use transistor This one is very standard MOSFET 2N7002 from diodes. This is a small one. Okay, I'm going to copy this one and I'm going to place it. So when we use this transistor, it means it will invert the signal, and it means that the LED will be on if the power output is not good one. So if there is error, LED will light up. Okay. Now the output, we are going to draw it here. So we are going to place their connector. I like this from Phoenix. We need 2 pins and look for this one, not this one. This is exactly what we would like to use. Okay. Copy and use it in our schematic. They have it in stock, so that's great. It's easy to connect this connector. Close to this connector we would like to place again 100 nanofarad capacitor for filtering, so I'm going to copy this and we will connect one pin to the USB voltage. So I'm going to copy the power symbol of the USB voltage, and the second pin of the connector is ground. I'm going to name this block as output connector. Now this is very important, so I'm going to write it down. The maximum output current and voltage depends on the power adapter, cable, and selected voltage. Okay, very important, so I'm going to make it red and bold. Save. Now we are going to do something extra with these configuration switches and configuration pins. We are actually going to show what voltage we selected. So here we are going to create a new block, voltage LED indicators or indicators. We are going to need LEDs. So I'm going to find green ones. I will just change this to G. Okay, they have green LEDs. And for every single voltage, we will have one LED to show which one is active. So we need one LED for 28 volts. I'm going to make it a little bit nicer. Now copy. We need one LED for 20 volts. Then 12, 9, and 5. Okay, be sure you connect the LEDs correctly. Okay, so this side of LEDs needs to be connected to ground. Copy and paste. I will also add this note which LED is for what voltage. So this one is 5 volt, 9 volt, 12 volt, 20, 28. Okay, this is just for us. I'm going to make it a little bit nicer. Maybe like this. And we also need, of course, series resistors to limit the current which is flowing through the LEDs. So again, I'm going to use this 1K resistor because I know the brightness of the LED will be then just right. Okay. Sometimes you, or normally, or very often, you may use also smaller resistors, like, I don't know, 500 ohms or even smaller ones, but then the LEDs may be very, very bright. That's why I use 1K resistors. Okay. And now we need something very clever. So I'm going to find this integrated circuit, interface, multiplexers. We are going to use this one channel, in stock, apply. And let's have a look if this is what we need. So open datasheet. And okay, so based on this combination of ABC, we can have only one output activated. That's exactly what we need. So I'm going to place it into our schematic. And then we have to connect it correctly, of course. But I don't like how this symbol looks. So again, we are going to adjust the look of the symbol. Go to library, find it in this project library. It is this one. So save it into personal library. Also the footprint. Find it in your personal library, and we are going to adjust the symbol. So edit device. The power is on the top, so I'm going to place it here. I'm going to adjust the shape of the symbol. Move the pins away so we have more space. On the left, we are going to place these inputs. So ABC will be connected to the configuration pins, and these are the inputs which will be connected to the output based on the combination of the ABC. So only one of these, X0, 1, 2, 3, 4, 5, 6, or 7, will be connected to the output X based on the combination of the ABC pins. So this is very easy way how we can, based on the configuration pins, we can very easily light up only one very specific LED. This is the output. VCC and VEE, I think they're both ground. We will double check a little bit later. I'm going to place our symbol into schematic. And now we have to connect it. So now first the easy part. So easy part is the power. For the power we would like to use decoupling capacitor, 100 nanofarad decoupling capacitor. Output is also easy to connect. It's going to be 3.3 volts, so we will be connecting 3.3 volts only to one of the LEDs. So VCCV, I'm going to double check, but as I said, I think they are ground. Yeah, okay, we can connect them both to ground. This was also easy. Copy, paste. Now the hard part. So let's have a look how it actually works. This table is very important. So this is our chip. And here you can see which output is activated based on what input. So I'm going to copy the configuration pins. I'm going to connect them to ABC. So C is going to be config 1, B is 2, and A is 3. And based on this table, you need to connect it like this. Okay, just do it exactly same way what I'm doing. If you would like to understand why it is connected this way, go to datasheet and double check these connections and the combinations based on the truth table in the datasheet. Then you will understand why we connected it this way. We have to connect all these together like this. Now this one, so it is basically enable pin. So it means when there is error, we don't want to show any LED on. So I'm going to use this power good signal, again also here in this chip. Perfect. For debugging, I'm going to connect also these I2C signals. So we will need a header. I'm going to use one of these, very simple header, SMD, right angle. We need 3 pins. Let's have a look what they have. Oh, this is exactly what I would like to have. This looks perfect. Okay, so copy and place it into our schematic. I'm going to move this little bit and we are going to connect these pins. So the middle one I'm going to connect to ground, and pin 1 and 3 I'm going to connect to the I2C signals. Again, this is just for testing and debugging because it can be super useful. There are some registers inside and you can play with some settings. So I2C header, and of course we are not going to fit it. Perfect. I'm going to add a note so everyone knows why we placed this header here. So it's just for experimenting. Now, what else is missing? Do you know? Mounting holes. So we are going to learn how you can create your own components. Go to File, New Component. I'm going to call it like this, MH 7.5 by 2.7 millimeter. It's going to be very simple component, just one pin. I'm going to hide the name and draw a circle. Maybe make it smaller and move it at the end of the pin. And I'm going to also change the line width, and I'm going to fill it up. Change the grid so we can move this little bit. Change the grid back, very important. It's not going to be in BOM, bill of material, and the designator is going to be MH question mark. Save it. New footprint. So this is going to be the physical interpretation of our mounting hole. Basically the part which is going to be in PCB, and mounting hole is basically just a path. Number 1 is very important because we have pin 1 in schematic, so it has to be pin 1 also in the PCB. And I will adjust the size of this path. And that's it. Very simple way to create mounting holes. We are going to assign the footprint to our symbol, and we can save our component. Close. Now go to library. Here is our mounting hole, and we can use it in our schematic. We will connect them to ground. They are already gray, so they are not included in BOM, bill of material, because they are not a real component. They are just PCB components. Okay, maybe move it a little bit. Okay. Save. I'm going to add also information about the license. I just do it, it should be there. And we can save our schematic. Now notice these reference designators. I'm going to remove them or clear them. So what was going to happen? They are now question marks instead of numbers. And manually I'm going to name the important components. So this one is J1. This one is going to be J2. So connectors are usually J. And this one is J3. Now, this one, the main chip, I would like to have U1, power supply U2, and this multiplexer U3. And all the other components, we can name them automatically. So go to Design, Annotate, watch what's going to happen, okay? See, now there are the numbers. Okay, you can see how my schematic designators look. Save. Now we are going to check if there are no errors. So you can do it also from this bottom toolbar. This one is not important, it's only warning. So it's perfect, there are no errors. Save, design, update, PCB. So this is the very important step. We are going to import all components from our schematic into our PCB. We can have a look, 3D view. So these are the components what we need to place on our board. I'm going to close this. And before we start, don't forget to set the units and the grid. And the very first thing what we are going to do is we are going to create the board shape, board outline. Draw it like exactly what I do. So from the 0, 0 position, update these numbers, and then your board will look exactly same as mine, and it will be easier for you to follow the layout what we are going to do. Now if we go to 3D view, you can see this is the board what we are going to create. And these are the components what we need to place on our board. Don't forget to save. We would like to work only with components. Change the grid size. And first I'm going to place these mounting holes. watch the position. Okay, this one is mounting hole 3, this one is mounting hole 4. Now the USB connector, place it here. Okay, manually you can write the position here, so you have it exactly in same position as I have it. Again, it will be easy for you then to follow the layout, what we will be doing in this video. And for this output connector, again, you can manually put the position here, do it exactly same way as I have it. Select everything, and we would like to lock them, so we don't want to accidentally move these components. Now this is the chip. So I'm going to place it here, 810, 730, and rotation 90. This is the regulator. You can place it into same position. This is the multiplexer. Okay, and these are the switches. Okay. We can also place this, but put it on the bottom, because by default we are not going to fit this connector and there is no space on the top side of our PCB. So we place it on the bottom side of our PCB and we can have a look how it looks. Okay, so on the top there are all the key components, and on the bottom there is the I2C header. I'm going to change the grid again. We are going to place the LEDs. So LED 2, so this is the 28, 20, 12, 9, 5 volt LED. And I'm going to move it a little bit like this. Okay, watch the position. So LED 2 is here. This is LED 3, 4, 5, 6. Now, components around this USB. So this capacitor need to be placed close to this USB connector. And these blue lines, they are telling you where the paths needs to be connected. You can see the blue lines, they go to the connector now. This is the position. You can use same position for easy layout later, okay? See, these are the lines, blue lines. When you hover a cursor over the path, you can see where the net is connected. I'm going to change the color of the ground net. I'm going to use this blue color. Then it's very easy to see what pins are connected to ground. But the color of the bottom layer is very similar to the color of the ground pin. So I'm going to change the color of the bottom layer to be like light blue. Watch what's going to happen. Okay? Okay, this is much better. But still, these reference designators, we would like to maybe hide them. So we would like to work with all the components and watch what's going to happen. Okay, we are going to hide the reference designators because they were a little bit annoying. They went over the paths. Later we can just enable the reference designators which are important. We don't really need them for layout. I'm going to also change color of this 3.3 volt net. I'm going to use this orange. And also for this one I'm going to use something like this. Okay, now we can see all the power and ground pins very nicely. Now this ESD protection, it has to be close to the USB connector, and I'm going to change the angle, maybe like this, and move it. Also the second one. Change this and move it. You can see how they are connected, okay? Next, we can place this 1K resistor. It is this one. So, watch the blue lines. You can see where the resistor is connected. We can place it here because there is a lot of space around the chip. So we can place it here. Then the coupling capacitor needs to be close to the pin number 1. That's the power pin here. So we would like to have it close. What else? These pull-up resistors. Where they are? Here. Okay, so I'm going to place it here. We can place all these resistors close to the multiplexer chip. So I'm going to put them one by one here. Because they are all connected to these pins which are connected to the multiplexer. Okay, you can see how they are connected. Always double check with cursor. Hover it over the pin, you will see, or hover it over the pad, you will see where the pad is connected. This one, okay, maybe this one we would like to place somewhere here. Okay. This one. This is the LED. The resistor, we would like to place it close to the LED. Maybe I will rotate this. Press spacebar to rotate, okay? Same as in the schematic. And transistor. Okay, pull up on power good pin. I'm double checking where everything is connected. This is the capacitor close to the output connector. Maybe rotate. Again, watch how it is connected, okay? Now these series resistors for the LED, so they are going to be close to the multiplexer. Okay. We could place them also close to the LEDs, but I didn't want to place too many components around the LEDs, because then I think when there are only the LEDs, it looks nicer. This one. And decoupling capacitor, again close to the power pin. Perfect. Save. What else? Okay, input capacitor for the regulator. It has to be close to the input pin of the regulator. Now the resistor on the enable pin. You can just place it here. And the output capacitors, they need to be placed close to the output from the regulator, like this. Okay. These are all the components. This was very easy and quick. Double check in 3D view. So this is how our board is going to look. Do you like it? Well done. Before we start doing layout, we would like to set rules. So design rules. We are going to use mills. Now search for JLC PCB capabilities, because we are going to use JLC PCB to manufacture our board. We would like to know what they can do. And we are going to double check the minimum track width and minimum clearance. So for multi-layer PCB, it is 3.5 mil. That's the minimum what they can manufacture. We are not going to use minimum. I'm going to change this to 10. But be careful, some of the numbers need to be a little bit bigger. So even I change everything to 10, I'm going to adjust this to 12. And we can make also this a little bit bigger. And this one a little bit bigger. Now for the minimum track width, again, we are going to use 10, not 3.5. That's the minimum what they can do. And for VIA, 24 and 12. Use exactly same numbers, okay? Now go to Tools, Layer Manager, and we are going to use 4-layer PCB. The layers inside of our PCB are going to be ground planes. So watch what's going to happen. Here are the inner layers. When we select it, double check if they are connected to ground. So this one is, and this one is also ground. Perfect. We can hide them, we don't need to see them. Go on the top layer and save everything. Before we start drawing, be sure you have same grid, be sure your top layer is active, zoom in, use mouse wheel, and track width is going to be 10 mils. Or press tab, you can adjust the track width. Then just left click, left click, left click. Okay, so this is how you draw connections on your PCB. It's very simple. Just left click on the path, left click and left click. I'm going to interrupt for a moment. If you really like this tutorial and you would like to learn more about electronics and how to design boards, check out our online courses. You will find everything important there, from basic board design up to advanced hardware design and high-speed PCB layout. We have courses in Altium, Cadence, KeyCut, and also courses covering many different topics, for example, FPGA, EMC, measurements, and so on. Visit our website at fedevel.com. Now we can go back to our tutorial. Let's continue. Okay, so watch where these are connected. What we are going to do, we are going to use vias. So we are going to change the layer from top layer to the bottom layer. That's what via is doing. Be sure it is 2412 mils. I'm going to copy this. Right click, copy, and now click on the path. Very useful. When you click on the path, you will be holding the selection where the path was, and then you can very simply paste it on next path. Okay. Make the grid a little bit smaller and draw the tracks maybe like this. Press shift, you can hold the shift down, and then it will stay in line. When you are drawing, it will stay in line. Try holding shift, what is happening. I'm going to place vias also here, and we also need to connect these to the resistors. So continue drawing on top layer and connect these resistors. Okay, perfect. You can easily adjust the shape of the track when you just hold left button on your mouse and then just move the track. Okay, we are going to connect these. Again, very simple connection. Left click, left click, left click, left click, and connect also these. Okay, where this is connected. It goes up. So what I'm going to do, I'm going to place a via here, and later we will connect it. Because there will be a lot of tracks crossing, so that's why we would like to go on the bottom layer. This is a very simple connection because we have, inside of our PCB, we have two ground layers. So everything what we need to do is just place very short track and connect it to ground. Notice for the powers and for the ground, I'm using wider tracks, 20 mils. So just press tab on your keyboard, you can adjust the width of the track. Okay. These are also very easy to connect, so let's do it. Here is ground. This is power. Okay. You can see now why we use the colors on the net, because it's very, very clear what is connected together. And using colors for power nets is especially useful because there are many power nets, many pins which are connected to power nets. Okay, we can connect this on the bottom layer. So that's why we are using via. These are ground pins, so this is very simple to connect. Just place via and it will connect to the middle layers, which are ground planes. I'm going to show you how they are connected. So if we go on this inner layer, watch what's going to happen. Select rebuild, and you see here is a space and there is no space. So you can see the ground vias are connected directly to the plane, ground plane. Now on the bottom layer, we can connect these together, and we still need to place there also a via. See, this is on the bottom layer, so we need to place a via here. Make it a little bit wider. You can very easily switch between views of different layers, or what you can do, you can actually use Shift S. Okay, try Shift S multiple times. This is Shift S view. Very useful. So only the active layer has the colors, the other layers, they are gray. Change the width back to 10. Okay. And connect these pins here on top layer. Now place a via. Okay. Now go on the bottom layer and connect these two vias together. Okay. Go back on top layer and we can continue. So the ground pin, that's too wide. I'm going to double check what is the width of the path. 15. So I'm going to use 15. So the track is not wider than the path. And this one, we have to place a via here, because on the top layer you can see there are the 3.3 volt tracks already. So we have to go on the bottom layer and connect the LED. Okay, very simple connection. And also we would like to connect this. Okay, these are all ground pins, so use wider track. They are connected to the layer 2 and layer 3. We can copy these because they are all exactly the same, and we can paste them on the paths. Okay. Perfect. Now the power. And place all the vias. Always before you start drawing tracks in specific areas of your PCB, always place all the vias, because then you will see where the space is. It means if you don't place vias and if you draw the tracks first, then what may happen, you will need to redraw your layout later when you will be placing the vias. But these are all very easy connections. So this is not like super critical how exactly you will be drawing the layout. There is a lot of space. And the connections are very simple. Okay, we need via also here. We can connect it. One more via here. Connect. I'm double checking what else we need to connect together. So this one goes here. Connect it also here. And on the top. Perfect. Next one. These are the ground pins. So before I continue routing in this area, I'm going to place these vias. And then we will do the layout. Because, you know, if I don't see these vias here, maybe I would route through this space. But now I see there are these vias, so I will go around them. And then I don't have to reroute what I already routed. Okay. So from the chip, go somewhere here and connect the header. and connect also the switches. And we also need to connect the multiplexer. Okay. Looks good. Now we can connect the LEDs. So this is simple because all the ground fan outs from these LEDs will be exactly the same. Just select it, copy, hold it where the pin is, and place it on another pin, next pin, next one here, and then here we also need vias. So same as before, do the fan out, copy it, and paste. So this very short connection from the path to via, it is usually called fan out. Now on the bottom layer we can connect all these. Just watch where every via is connected. With this one we will go a little bit around. And also notice I keep a big space between the tracks. That's a very good habit. For this PCB it's not very important because these signals are not like high-speed signals or some very important signals, but it's a very good habit. Do not route these tracks or do not draw these tracks very close to each other. If you have a lot of space on your board, on your PCB, then keep big spaces between the tracks. The reason is crosstalk. If you like, you can search for meaning of crosstalk, but basically if you route signals very close to each other, then they can influence each other. The noise can be picked up by the neighbor traces. But again, as I said, for this PCB it's not important. There are no really signals running through these tracks. These are just, switches, or the most important interface here is the USB interface. And then we have there also I2C, but I2C is also not like super high speed or difficult to route. Okay, let's continue. So we have to connect this exposed path to ground, and I use more vias because they can also take heat away from the chip. So if the chip, in some situations, some chips, they may get warm or hot, so it's very useful to use multiple vias. This chip may not get really hot, but again, it's a good habit. Place multiple ground vias into exposed path. Okay. We are going to connect a CC1 pin, draw a short track and place a via. So this is fan out of the CC1 pin. Now USB, again fan out for USB, track and via. USB interface is very important, so we will have to place here also something what is called ground stitching via. So let's do it. If you would like to learn more, just watch my videos. Oh, this one doesn't have the correct net connected, so I'm going to connect it to ground. And there is error. You can see these yellow crosses. It means there is error. So the track was very close to the via. I moved it away and then error disappeared. Save. We are going to connect this USB power, change the width to 20 mils, and there is a problem. There is violation. To fix this violation, I'm going to create this special region. It is just a special rectangle, which I'm going to draw around these paths. I'm going to call it USB-C. Remember this name, okay? Then, inside of rules, I'm going to create special spacing rule. I'm going to call it USB-C clearance, and inside of this rectangle we will set special smaller clearance 6 mils. Okay, I'm going to double check. The minimum is 3.5 what we can use in JLC. 6 is bigger, so it is fine. And now in this USB-C region I'm going to assign this new USB-C clearance rule. Okay, this is the rectangle what we created. Confirm. Now let's try it again. So I'm going to route the USB power, and you can see we can do it. I'm going to select this and I'm going to change it to 20 mils. Okay. Right now we are just drawing these connections to connect all the pins, but a little bit later when we will be finishing this design, we will actually draw big polygon. So this is just to see where we need copper for this USB power. Now CC1 10 mils. We need to place a via here, and we can connect it on the bottom of our PCB. You can do it like this. Okay, now CC2, it goes up. So I'm going to draw this short track, place via, and connect on the bottom. But there are these USB signals, so I will go actually around this way, okay? Because a little bit later we will route USB signals in this area too. Perfect. Now the ground. There are many ground pins. So before we start routing the USB signals, we would like to see where is the space. So we are going to put there all the vias. Okay. Next one. Let's connect this. Then this one. Maybe like this. Also here. When you use spacebar, you will change the angle how the track suggestion is made. So when you are routing a track, try space, you will see what will happen. Okay. Now I'm going to continue routing this USB power. So I'm going to connect all these pins. And as I said, a little bit later we will draw big copper plane for this USB power. So it's not really super important how these tracks look. Now this, maybe I would like to swap these two pins. We would like to have maybe power on the top and ground on the bottom. But we can't just simply rotate the connector because there are the openings for the wires. So what we need to do, we need to go into schematic actually and swap the pins, and I'm going to show you how to do it. This is very useful to know how to do because we already finished the schematic. So this is how you can make schematic changes later. I'm going to swap these pins, watch what's going to happen, and I'm going to connect everything again. So now pin number 2 is on the top and pin number 1 is on the bottom. Save. Go to design and update PCB. Okay, we made changes in schematic. Here you can see what kind of changes we made and watch what's going to happen. Okay. Good. Apply. Watch. Perfect. Okay, so if you need to do any changes later in the schematic, this is the way how you can do it. It's very, very simple. I'm going to connect these pins which are connected to power, and then this USB power is finished. Ground. Now this pin, it still shows it is not connected, so I'm going to rebuild this ground plane which is inside of our PCB and watch what happened. Okay, now it's connected to ground plane. Okay. Save everything. And what left are these USB tracks. So go to fedevel.com/hardwareassistant and we are going to ask question. We need some help with doing layout. This is actually our AI assistant, so if you have any questions you can try it. So what is important when routing digital tracks and USB signals? Important is impedance. So for digital tracks, the impedance is 50 ohms usually, but for USB signals, it is 90 ohms differential per impedance. Okay, so 90 and 50. Remember these two numbers. What does it mean? It means we have to go to the JLC PCB impedance calculator, and based on the Stackup, based on the PCB what we are going to use, we need to calculate what is going to be track width and space between the tracks for 50 ohms and for 90 ohm differentials. So you can do it this way. Okay, this is the Stackup what we are going to use, this one which has like 0.09 millimeter distance between layer 1 and layer 2. And for standard digital tracks we would like to use this 6.1, and for the differential pair 6.2, track width and 8 mils spacing. Okay, so I'm going to create a special rule for differential pairs. What do we need to use? 6.2 for track width and for the space between the two tracks 8 mils. Okay, so that's why we needed the impedance calculator, so we can use these numbers here. This is okay, we can leave it. Now, we have to specify which of the signals are differential pair signals, so I'm going to find them in this list. I'm going to create new differential pair, and so this one is positive, and this one is negative, confirm. And then to these signals, we can assign this differential pair rule, which specifies the track width and the space between the tracks. We did this because then it is much easier to do the layout. Watch what's going to happen. When we go to route and differential pair routing, then if we follow the rules, the track width will be automatically set to 6.2, and also the space between the tracks is automatically set to what we specified. We can adjust this a little bit, maybe like this. Or maybe not. Okay. And if you select this, you can see it is 6.2 mil wide. And I'm going to change the grid size so we can measure this very precisely. So when we measure the distance between these two tracks, you can see it is 8 mils. So based on the rule what we set, we can now automatically route these differential pairs. It is very, very useful to set this kind of rule. Okay, so let's finish this USB routing. You can do it maybe like this. I go far away from the other signals. Okay, perfect. Maybe little adjustments. Now let's go on the top, and you remember this is a little bit wider, so I'm going to change this to 6.2, and also this one. Okay. What left is this connection here, and this is not exactly how I like to route USB differential pairs, because they should be routed properly, but there is no other way to connect this USB-C connector. Ideally, you would like to have just nice, two tracks routed together, but these USB-C connectors, they are designed the way that we have to connect it like this. Not the best way to route differential pairs, but as I say, there is no other way to do it. There is one unconnected path, but I would like to show you how you can run DRC check. So when you run DRC check, you can see all the errors in your PCB. These are clearance, differential pair, and this is the connection error. So it is telling us there is something not connected, and you can very easily find it. So when you finish your layout, run DRC check and double check if you have everything connected. Now watch what's going to happen. I connected everything. It's gone. Okay. Now everything is connected. Well done. So even everything is connected, we still have many errors. So if I go back to DRC, there are many errors with this inner plane. Do you know what is the problem? The problem is we need to rebuild these ground planes inside of our PCB, and that should fix many, many errors. Watch. Okay, now go back to DRC, clear, and rerun. Perfect, there is only one error, differential pair, and this is very easy to fix. Basically, this is telling us that the USB is not properly routed in the length of 25 mils. See, so we just need to change this to a little bit higher number, and then the error should disappear. Oh, perfect. These are the tracks which are not routed as differential pair, so that's the length what we had to adjust. There is still problem with this chip. I received email from JLC PCB and it says it takes 34 working days to get the chip. Yeah, if you go to schematic and if I copy the part number, when we go to LCSC website, you can see they still don't have it in stock. If we have a look inside of datasheet, then they have two basically same chips, this A and Q version. They are exactly same. Watch the pinout. Okay, just the Q has different footprint. And if we have a look, if we try to search for the Q version, they have many in stock. So maybe what we should do, we should just use this Q version. And that's what I'm going to do now. I'm just going to change it in our schematic. So I'm going to save this. I'm going to save it as a new version because I'm going to make big changes, okay? And later, in case I would like to go back to this A version, I always can do back. I always can go back. Now I'm going to copy the part number of the Q version and I'm going to place it into our schematic. They have it, so that's good. But they look different, the symbol looks different, so ideally what we would like to do, we would like to update the symbol, make it exactly the same. So I'm going to save this component into my personal library and we are going to adjust the shape of the symbol. We will make it exactly the same and then we can basically do very easy replacement in our schematic. Okay, so on the top is going to be the power. I'm going to delete this. Adjust the size, make it look exactly the same as the one what we have in schematic. So move this away. Do you remember how it looks? V bus on the top, positive, negative USB signals, CC1, CC2. Now config 1, 2, 3, power good, and ground. Be sure all the pins are exactly in the same place as in the other version of the chip. Okay, save and close. We can delete this one. Go to personal library and we are going to place the new symbol. So this is now the Q version of the chip. I'm going to change it to U1. Okay. We can delete this old one, the A version of the chip, and we can place the new one here. Remember the position of this one. I'm going to delete it. Confirm. Now, save everything, go to schematic, design, and update PCB. We are going to add the new chip, and here it is. It is much smaller, and this one they have in stock, So it will be very easy for us to build the board. I'm going to place it exactly into same position as the original chip. Okay, also change the rotation. Perfect. And we may need to do a few small adjustments because you can see there are many errors, many yellow crosses. So first I'm going to delete these vias. And there are many new errors. So this is clearance. I'm going to double check what we need to set. So it is 10 mils is expected, but it is actually 6.9 mil. So I'm going to adjust our spacing rule, and I'm going to make it smaller, okay? Between the tracks and between the pads, I'm going to use 6 mils. Now when we double check, they should disappear. Perfect. We just need to reconnect everything. So I'm going to connect power. The width of this pad is 8.8. So I'm going to use 8 mil track width. And I'm going to connect this. But we have to change also the minimum track width in our board. Right now it is 10, but for 50 ohms we would like to use 6.1. I'm going to change it to 6 mils, so later when we will be adjusting the track width for 50 ohms, we will not see any errors. Now I can easily change it to 8 mils, and I'm going to move this white track a little bit closer to our chip. Same here, 8 mil track, and I'm going to connect it to this decoupling capacitor. Maybe make it a little bit nicer. Use white tracks. Like this, maybe. Okay, connect CC1. 6.1, that's the 50 ohm impedance, okay? 6.1. A little bit later we will adjust all the tracks to 6.1, you will see. So don't worry that it looks a little bit weird right now, like part of the track is very thin and the other part of the track is white. Connect all of them. So basically this design is going to be universal. So in case you would like to use the bigger chip later or in the future, you still can do it. You just change the footprint back as what we had before, and you can have a board which also supports the other chip, the A variant of the chip. Here I'm going to delete this and route differential pair and connect it. Okay. Okay. Save. I still don't like this. Maybe I'm going to move this decoupling capacitor a little bit closer. This is going to be better. Because the decoupling capacitor should be always as close as possible to the power pin of the chip. So I like this a little bit more. Okay. Perfect. Here, what we would like to do, we would like to make this copper a little bit bigger. Okay, so I'm going to draw this rectangle, and I'm going to connect it to the ground net. Confirm. And notice these weird connections. We would like to have direct connections. So here in this copper region, for the single layer path, I'm going to change it to direct. Now select it and redraw. Okay, this is what I would like to have. And I would like to place one more via here and one more via here. I don't like this, so I'm going to move it a little bit away. Oops. Because the copper from the rectangle is cut out because the track was very close to the rectangle. Maybe do it again. Like this. Okay. Now when you select it again and redraw, now it's better. Okay. Watch what we are going to do with this 3.3 volts. I'm going to draw this copper region. Watch the position of my cursor. And basically what we are going to do, we are going to replace these tracks. We are going to replace them with copper area. And that's what I normally do for powers. For powers, I very often use these copper areas. So just draw it same way as I do it. If you don't do it exactly the same way, you can always adjust the shape a little bit later. So don't worry if what you are drawing doesn't look exactly as what I'm drawing. Just finish it, and a little bit later you can adjust the shape. Okay. Be sure it is connected to 3.3 volts. If not, then you can do it, you can fix it this way. Okay. Now we can do exactly the same here for this ground in this corner, because this small regulator, it can get warm, and these big areas, they are very useful taking heat away, because the input voltage can go up to 28 volts, and this chip, it has to create 3.3 volts from 28 volts, so there could be a lot of heat generated inside of this chip. So if we use this big copper area, it can help with taking the heat away from the chip. And that's why we are creating this big area for the ground, and also we created this big area for the 3.3 volts. Both these big areas will help. Okay, be sure this is connected to ground. And this is very thin for ground. We are going to adjust the width of these connections. So here in multi-layer path, change the width to 20. Watch what's going to happen. So select and rebuild. Now it's wider. Okay. Save. Now the USB power. So draw copper region all around the power. So this connection, it can, I think for the USB, the limit is like 5 amps for some of the specifications. So quite a lot of current can actually flow through this connection. So we would like to have it, we would like to have this connection as good as possible to handle these higher currents. The standard USB is the one what you have on the PC is usually only half amp, but this USB-C, especially with these power delivery capabilities, it can go up to 3 amps or it can go up to 5 amps based on the power adapter what you are using. Just draw it around all the paths. You can do it exactly the same way as I do it. And it's almost finished. This is the biggest one. Okay. Be sure it is connected to the USB power. Okay. And we will make a few adjustments. So I'm going to change the grid to smaller one and select the polygon and just move the edges of the polygon. Maybe I can move it like this. Okay. Looks good. Maybe here I would like to make it just around the path. Rebuild. And don't forget to go back to 5mm grid. Save. We are going to learn something useful. Watch this polygon. The copper of this polygon is a little bit deeper because it's influenced by this ground polygon. If you go to Tools, Copper Manager, you can actually change the priority of the polygons. So this one is on the top currently, this one is on the bottom, and I'm going to move it up. Okay, so watch what's going to happen. So first the USB power polygon is created, and then the ground polygon is created. Now we would like to have direct connection here. I don't want to use these wires. So I'm going to add a new rule for the connection of the region. And for single layer path and also multi-layer path, I will set it as direct. And then when we go to these net rules, copper zone, we will find the USB power and we will use this rule. Okay, now select it and redraw, and now it has direct connection. Okay, we are going to check the connections on the inner layers. For example, this is very thin, also this one, or very narrow. So I'm going to change, this time it's going to be plain rule. We will keep it as spoke, but we will make it wider, 20 mils. Confirm, select, and of course rebuild. Watch what's going to happen. It is wider, perfect. Also do it for the layer 3, rebuild, and it's wider. Okay. As I mentioned before, we would like to use 50 ohm impedance, which is 6.1 mil trace width for all the other digital tracks. So this one is 6.1, but this one is 10 mils, see? So right click, find all the tracks with 10 mils width, okay, and find all. You should see all these 10 mil tracks selected, and simply just go here and change the width to be 6.1 mil. So this way, what was going to happen? This way we actually changed all the tracks to be 50 ohm impedance, all the digital tracks, except the USB. See, USB is still 6.2 for 90 ohm differential pair impedance. We finished the layout, we connected everything, but we still would like to maybe do some adjustments in Silkscreen. Silkscreen is usually the white color on your PCB, and usually there are like designators and text and some notes. So first I'm going to enable designator of this USB-C connector. You can see it is called J1, and I'm going to double check what are the capabilities for Silkscreen when the PCB is manufactured in JLC. So minimum line width and minimum text height 6 and 40 mils. So I'm just checking 6 and 45. It's okay, they can manufacture it, but we can make it a little bit bigger. Okay, 40 is very small, so I'm going to use 80 mils and I'm going to place it like this. Same for this output connector. I'm going to enable the designator and I'm going to make it a little bit bigger, 80 mils, and maybe place it somewhere here so it looks nice. Next, we are going to work only on the Silkscreen layer, and I'm going to add the description for the LEDs. So you can use exactly same size of the text and same parameters of the text. I'm going to change this to center bottom because then it will be easy to align the text with the LEDs. Check the position. I'm going to copy it from the middle of the LED and place it on the other LEDs. Okay, and now when we adjust the text, it will be correctly centered. This one is going to be 20 volts and the last one is 28. Okay, be sure it is correct. Okay, I'm selecting this LED and just double checking if the description of the LED is correct. Okay, perfect. Now copy and just paste somewhere. I'm going to put here text, output, voltage, so everyone understands what these LEDs are about. Okay. What else? Maybe we can put there more nodes. For example, we can put here a node like input, okay, and then output on the second connector. And we do it because everyone who is using your boards, they should be able to use them without actually looking into manual. So if you can add information which is useful for everyone who is using your board, just add these notes, add this text. Okay. Let's have a look. Cool. We are going to add some information about these switches. It is a lot of empty space. So first I'm going to make it clear where are the switches. So I will just place the text here, and we would like to also tell everyone which side of the switches is 0 and which one is 1. So when the switch is in the bottom position, then it is 0, and when the switch is in the top position, it is 1. Because on the switch itself it says on the top it says on, that's why I use 1 on the top. Okay. And now we need to add the table which describes the position of the switches and the selected voltage. So again, we are doing this because people should be able to use our board without looking into manual. So ideally we would like to put all the information about the switches and the selected voltage directly on the board. It's very simple to do, we have a lot of space on the board, so why not? Okay. So this is going to be switch 1. Switch 2. And switch 3. This is the output voltage. Okay. Now we have to put here all the 1s and 0s. So first I will prepare this here. I'm going to copy it for every single line, for every single voltage, and then we will change everything at once. Okay, go to schematic, put here all the voltages, (20, 28), and now be very careful, this is actually not 1, this is 0, okay, and this is not 0, this is 1. So for 5 volts we need to put here 0, 0, 0. And the reason why it is this way is because how I mark the 0 and 1 position of the switches, okay. So we have to put it this way on the Silkscreen of our board. So for this one it's going to be 1, 1, 0. And for this one it's going to be 0, 1, 0, 0. Okay, and the last one is 1, 0, 1. Okay. Now here we would like to see what is plus and what is minus. So very simply I'm going to add big plus here. You know, when you are connecting wires, you would like to clearly see which of the pins is plus and which one is minus. That's why we would like to put this information directly on the PCB. We still have some space there. So this one is minus. Okay. And let's have a look. Very cool. Now this LED, we would like to put also some information about the LED on the board. So you know it is error LED, so I'm going to put here error text, so everyone knows when this is on, there is something wrong. And we will explain what the problem is, okay? So I'm going to put here more text, and I'm going to explain, check if your power adapter supports PD, okay? So copy this and continue. Check if check if USB-C adapter supports PD. Okay, perfect. Now let's add also some information on the bottom side of our PCB. So I'm going to enable this designator, but it is mirrored, see? So go to view and flip board. So this is the way how you can see the bottom side of your PCB. Now the text is correct. And I'm going to double check what is the size, what we use on the top. And we will use the same here. So this is J3 connector or J3 header. And also we could add information about the pins. We have a lot of space there. So again, I'm going to use some of the text that we already have on the top. I'm going to copy it, paste it, and I'm going to place it on the bottom Silkscreen. Okay. Now, maybe place it like this. This is the clock. Okay. Make it look nice. Copy. Paste. This one is ground. That's the middle pin. And these are the data. So when someone is using this header, they will immediately know what are these pins. Again, they don't have to use manual, they don't have to look into schematic. They just will know from the PCB. Next, we would like to add some information about the board itself, because sometimes you may have multiple versions of the board, multiple similar boards. So you would like to put the name of the board on the Silkscreen together with the version of the board. Okay, so this is USB-C Advanced power supply version 1 issue 0. Okay. And maybe you would like to also add copyright or information about your company. So I'm going to put here FEDEVO 2026. Okay. Very important, don't forget about this. I'm going to save everything. I'm going to remove this space. And what else we are going to add? Some advertisement. You know, because I'm doing these tutorials also, you know, to promote a little bit our company and what we do. So if you would like to learn more about how to design boards, we actually have a website with online courses, all the kind of different courses from Altium through KiCad, Cadence. The courses are for beginners, also for senior engineers, about all the kind of topics from like learning the basics, how to use different tools, up to EMC or measurements, and you know, very advanced topics like signal integrity. So don't forget, if you would like to learn more about electronics, then you can go on our website. Do you know what is our website? www.fedevel.com. Thank you very much. Okay, let's have a look. Cool. And there is this big empty space. We are going to put logo here. I need to move this a little bit because maybe it's not very symmetrical. I will just move it a little bit up. I think this is better. Let's have a look. Okay, a little bit better. Now, this is the picture with our logo. It is very simple picture. This one is black and no background, but you can also use black and white. Place image. Just select the image, open, leave this, set the size. Click here, this is very important, okay, and confirm. And this is basically the way how you can add any picture on your board. I'm going to double check if it's in center. I'm going to move it a little bit maybe, like this. And let's have a look. Super cool, very nice. And I'm going to teach you one more trick. We are going to again add logo, but special logo, gold logo. We are going to place it here on the top layer. We have to place it where the copper is, but we are going to basically do it through this top solder mask layer. So again, I'm going to use same image, and here on the top of the copper, we are going to place very small logo, and where the logo is, the solder mask is going to be removed. The color of the PCB is going to be removed. In this case, it is the blue color, but normally it's the green color which is removed. And if your board, if you use the anic finish, the gold finish, then this logo is going to be gold. It's going to look very, very nice, very cool. So if you would like to have gold logo on your PCB, this is the way how you do it. Okay, just remove the solder mask from the area, and be sure there is copper in this area. I'm going to add information about license because this is very important. Just copy and paste. I already have it prepared. I will just adjust the size and font. Okay. And save. There is this one thing which keeps bothering me. I would like to make this ground plane a little bit bigger and put there maybe a little bit more vias, because the chip is very, very small, and the input voltage is 28 volts. Maybe it can get hot, so I would like to put there more vias to help the heat disappear away from the chip. I'm not sure how hot it can get, but we have a lot of space around the chip, so we can add more vias. We can make this ground plane a little bit bigger, so why not? Okay, we need to assign the net names to these vias. And then we have to redraw the copper. I need to move it a little bit away. Okay. I'm going to delete the old rectangle, old copper pour. Just delete it. And I'm going to draw a new one. On top layer, copper region, polygon, and I'm going to draw it around these vias. Always when you think a component may get hot, then try to find a way how to put there maybe bigger copper or more vias in case you have ground planes, big ground planes inside of your PCB. Then these ground vias can take heat away and bring it into these big ground planes. It's very helpful. It helps a lot. You would be surprised. I remember once I had like 4 ground planes inside of my PCB, and I forgot to set a thermal relief. That's the star connection of the through-hole pins, which we adjusted before, you remember it. I forgot to make this thermal relief on ground pins, and it was extremely hard to solder down all the ground through-hole pins because there were 4 ground planes inside of the PCB. Okay, now I'm happy. Don't forget to change the grid size back to 10 mils, and also double check if there are no errors. Basically, we are finished. And before generating the outputs for manufacturing, we need to be sure everything is correct. So what we are going to do, we are going to rerun DRC check for schematic. There are no errors, just this one warning, but it is okay. We are going to be sure that the schematic and PCB are synchronized. So run this, update PCB. Perfect, no changes. Now in PCB, we would like to rebuild all the polygons. We would like to rebuild the ground planes inside of our PCB. And we would like to rerun DRC on PCB. Okay, everything seems to be fine, so we can lock our board. Go to Export, Gerber Files. Now export Gerber. continue, and this is the file what we have generated. Okay, these are the files which are needed to manufacture our PCB. I'm going to make temporary directory, and we are going to double check these files. So go and search for ViewMate. This is what I use to check Gerber files. It is free software. You can just download it here and install it on your PC. Once you run it, this is how it looks. Go to File, Import Gerber. Okay, I'm going to open the directory with the files what we just generated, and we are going to import these Gerber files. I'm going to order them by name. We are going to import them into this software. Click on the next layer and import also drill files. So these are the drill files. Import. Switch off everything. Switch on the board outline layer, and one by one double check every layer. So you can very nicely see the mask and paste layers. You can see the Silkscreen top layer. Everything seems to be fine. This is inside of the board. So the mask layer is the green color or blue color or red color. Silkscreen is the white color on the PCB, and the paste layer is the layer which is used for the solder paste for the SMD components. Okay, everything seems to be fine. Here are also the drilling. Here is the drilling information. So these are the vias. These are all the holes. These are not plated. Not plated, it means there is no copper inside of these holes. Perfect. It looks good. So we can actually delete this directory, temporary directory. We don't need it anymore. These are the this is the file what we will need for manufacturing. Next, export bill of material. So this is the next file what you need to manufacture your board. Be sure it is set same way as I have in here. Export BOM. So BOM is bill of material. It is list of all the components which are used on your board. When we open it, this is how it looks. Okay, you can see these are all the components, and here is the side of the PCB where these components are used. You can see these are all the fitted components. When we double check, this is unfitted, R8, R9, R7. These are unfitted, but because we marked them, they are not fitted, they are not included in this BOM. See, perfect. So this BOM was correctly generated. Okay, and there is one more file, pick and place file. Again, use exactly same settings what I have here. Click on export. This file is used for the machine which is placing the SMT components. So this is the file what we generated, and here are all the components and the position on the PCB. Okay, so based on this, the machine will know where to place the components. We are only going to place the components on the top side, and only the components which are fitted in BOM. So I'm going to remove all the components which are on the bottom. That's the header or the connector for I2C, and I'm going to remove or delete all the components which are not in the BOM. Okay, delete, save, and I'm going to call this top only. Save, close. So these are the files what we need to manufacture our board. Go to JLC PCB website, click on Instant Quote, and I'm going to drag and drop the Gerber files here. So this is our board, this is the top and bottom side. 4 layers. I would like to use red. Watch what's going to happen. The price is going to be increased. So if you would like to keep price low, just use the green one. And NIC, that's the gold layer on the PCB, okay? This is what will make our logo gold, but it is kind of expensive. Okay, because we are using which Stackup? 3313 Stackup. So we have to select it here. Confirm. Layer sequence should be okay. We will then double check it later. Remove mark, okay. Everything else here looks okay. We don't have to do anything here. Now, PCB assembly. So this is all about the components. So we would like to place components on top side of our board. Confirm placement. I always do this because I would like to be sure they will fit all the components correctly. Okay, next. Next. Now we need to upload the BOM, bill of material. So drag and drop it here. And also pick and place file. So this one, top only. Next. Okay, they have all the components. This is perfect. If they don't have all the components, don't worry. You can just buy them in your standard supplier and then solder these components later when you receive the boards. Okay, don't worry. You can see some of the components are not fitted, so that's correct. And this is the final price. I'm going to put here a note. What is this board about? They usually use this for customs, so you need to put here this information. And you can have a look. So this is the PCB price, this is the assembly price. This includes also the component price. So there is setup fee, stencil, components, feeders, all the kind of fees. If you don't want to pay for the assembly, you can buy all the components by yourself and then you can save a lot of money. Let's double check our order. So first I'm going to click on this edit order. And we can go to this Gerber viewer just to be sure these Gerber files were correctly loaded. We can go to these layers, switch off everything, and double check it. When I say that you can save a lot of money on the assembly, I mean you still have to pay for the components itself, but you don't have to pay the setup fees and feeder fees and some extra charges. So you can save some money if you assemble the board by yourself, and if you buy the green PCB, then it will be much cheaper than what you see, what I have here. Okay, you can double check also the settings on the PCB and also all the settings for the components. Here is list of the components. This is the placement. Everything seems to be fine. Select this and we can order our boards. So click here, continue. I'm going to use DHL, but you can use also this. It's cheaper, but it takes longer. Okay, there are some coupons, so if you like, you can apply one of these coupons. Why not? And let's pay. Once you pay, then you can always check the status of your order here. Now, what you can do, you can save this as a new version. In case you need to go back and check what you sent to production, you can always go and open this specific version. So don't forget, if some of the components are missing, you can just go to your supplier like DigiKey, Mouser, or Farnell, and you can buy the components and fit them a little bit later after you receive your board. Do you remember when we were ordering PCB, we checked the checkbox to let us know or to confirm the component placement? So that's what we are going to do now. And this is very useful because initially the component placement is not correct. You don't have to correct it by yourself, just leave it to them and then ask them, after they make the corrections, ask them to send you this notification, and then you can just double check if the component placement is correct. And they always make it good. I never had problems with this component placement after they check it. So we can just confirm this, and basically everything is ready. After 10 days, I received this package. And let's have a look what is inside. Our boards! Cool! So remove the panel. And let's have a look. So nice. Really, really nice. This is the back side. Okay, double check the soldering. Okay, be sure everything is soldered correctly, there are no short circuits, quality of the soldering is okay. Double check the unfitted components, double check pin 1 position on the chips. Remove this foil and be sure all the switches are in the bottom position. Now I'm going to use this special device. I've got it from NextPCB as a present, but you can buy it on Amazon. It's very, very useful device. Okay, it will show you the voltage and current going through the USB. And it works, 5 volts, and the LED is 5 volts, and the current is really, really minimum, so everything seems to be fine. I'm going to double check the output voltage from the regulator, 3.3 volts, and the input voltage on the regulator, 5 volts. Perfect. Now, I have this electronic load. I'm going to set 3 amps. Be sure the switches are set to 5 volts, and we are going to double check. So 5 volt, 5 volt, 5 volt. I'm going to switch on this electronic load. We should see 3 amps, 3 amps, and if we try different voltage, 9 volts, 9 volts, 9 volts, 3 amps is flowing. Next one is 12 volts. Next one is 20 volts. And I have to decrease the current because the electronic load is only up to 60 watts. Everything is working fine. Perfect. This is the power supply or the adapter what I used. And don't forget you have to use also this special 3.1 USB cable. If you use a different kind of cable, for example like this one, or different adapter, you can get different results. For 5 volts this one works. This one also works for 9 volts. Next one is 12. Okay, so don't forget this is different adapter, and some adapters they don't work for everything. Like this one, 28 volts. See, there is error. This adapter, what I'm using right now, or this cable, it can't deliver 28 volts. Okay. And this is different cable just from standard PC. You can see it says 5 volts all the time. Error LED is on because standard PC doesn't support power delivery. These switches, they don't work. Have a look. It doesn't matter what I do with the switches, it just doesn't work. So be sure you use correct USB-C power adapter to work with this port. Now go to datasheet, and there is something very interesting. There is this PPS voltage configuration register where you can set output voltage. So when you are running this chip in PPS mode, you can set all the kind of different output voltages. But to be able to run this chip in I2C, we have to run it in this single register mode. And single register mode, it means CFG1 connects resistors to ground. So if we go here, this is CFG1, and this is the resistor which by default we do not fit. It is this resistor. So what we are going to do, we are going to unfit this pull-up, it is this one, and we will fit the pull-down resistor to be able to use I2C and talk to our chip. So let's do this. We need to solder down this header, this connector. This is the device what I'm going to use. I will connect it to my PC. These are the signals, SDA, ground, and clock, and we will connect them here. So first I'm going to put a little bit of solder on each of the pads. I'm going to connect the cable because then the heat from the pins goes away, and the pins will not melt in the plastic. It's super useful trick. Now I'm going to remove this pull-up. Okay, clean it a little bit, and I'm going to put the resistor back, but as a pull-down. It is 10K resistor, it is not like 6.8 or what they recommend, but for this testing it really doesn't matter. So if you don't have the exact 6.8 K resistor, you can just use the 10K. For the testing it's fine. So this one is not fitted, this one is fitted. Be sure the switches are in the bottom position. Now I'm going to start this control center, and I'm going to connect this I2C device, what I'm using. Okay. We are ready to test it. So be sure you connect all the wires correctly. So SDA, ground, and clock. We are going to connect it to USB. And now ignore these LEDs, okay? They don't work correctly. Just ignore the green LEDs. The address is 22, so here is 22. And these are the registers, 9 and A. So I'm going to read from the register 9, 8 bits. So that's 88, and 01 is basically this, what is inside of this A register. It means 9 volts, see? Now if you like to put there 12 volts, then we need to put there number 2. So in register A, we need to put number 2, right? See, 12 volts. 15 volts, we need to put here number 3. And watch, right? 15. But what is more interesting, it is to play with this voltage configuration register. I'm going to switch to this batch mode because we need to write multiple values. It is very simple script. At the beginning, we are just doing I2C initialization. Then there is the default setup, 5 volts. So here in this A register, we will enable 5 volts. And a little bit later, we are using this voltage configuration register to set the output voltage, okay? And I made this very simple table. So here are the numbers what we need to put into the register based on the voltage what we require. And the last value what we will run will be 6.7 volts. So these are all the kind of voltages what we will see on the output, from 5 volts up to 20. Watch. 6, 7, 8, 9, 10. Okay, we are setting up all these voltages through the voltage configuration register. And the last one is this 6.7 because I wanted to show you can actually set any kind of voltage. Okay, so it's the number 43, you can see 6.7 volts. Now we are basically finished, but there are still few words what I would like to say. So first, if you search for Fedevel GitHub, go here, and I created this USB-C Advanced Power Supply repository. Here you will find all the information about this project, okay? So even in future, if I make any changes or anything, I will post all the resources, all the links on this project. If you are building this board, have a look here, because maybe you will find here something what, I don't know, something new, something what can be useful for you. And also, I'm going to create this project also on this OSHW lab. This is basically a website which is connected with EasyEDA directly. So once you see the project listed here, you can very easily clone whole project. You can open it in EasyEDA, and you can just continue modifying and improving this board. So this will make it very easy if you like the board and you would like to make some changes for yourself. And that's everything for this tutorial. I really hope you design and build your own board. Let me know, okay? Let me know in the comments. And don't forget, if you would like to learn more about electronics and how to design boards, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC, measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.